Hey, welcome to video notes 9.1. We're going to be doing a lot of defining in this one and explaining. So get ready to write. Okay. So it'll be a tidal wave of notes. Get it? Alright, so look for the book connections. Look at some pictures. It'll help. Alright, so let's talk about water. Okay, so water is really pure, but usually a solution. So we defined this in class. We did talk about the two parts, though. The two parts of a solution are the solute, which is the smaller part, and the solvent, which is the bigger part. Miscible refers specifically to two liquids that can mix. Okay, so can make a solution. So make sure you know how to use the vocab. All right, so water and vinegar mix to make a solution. If there's less vinegar than water, then vinegar is a solute and water is a solvent. You get dissolved. That's how I remember that the solute is the smaller part. You get dissolved. Okay, so all solutions are homogeneous mixtures. We talked about all of these already, but make sure you can think of at least one of each kind. Okay, please make sure you know. All right, so 4 major questions we're going to ask ourselves in this unit. Question 1 is, will it dissolve? Okay, to make a solution. So will it dissolve? We looked at these in class, but so what does dissolve? If something is polar, if a molecule is polar, it should dissolve in another polar solvent. So polar solute dissolves in polar solvent. Ionic solute dissolves in polar solvent. Nonpolar solute dissolves in nonpolar solvent. And polar does not dissolve in nonpolar. Okay, so what is this? This is nonpolar because these bonds are nonpolar, so there's no dipoles. So this is nonpolar, so it should dissolve in a nonpolar solvent, or it could be the nonpolar solvent. Nonpolar again, nonpolar solvent. Polar and polar. Okay, so what is the Wicked Witch? You tell me. Okay, you tell me what the Wicked Witch is. She had water poured on her. And what happened? Okay, so translation and words to live by. When it comes to solutions, please try to remember like dissolves like. Go back and see if you can plug in words that go here to help understand that. Okay, and then shout out to Matt, and he likes to swim, and he's always in class, even after swimming. So what do you think? Is Matt polar or non-polar? Okay, so think about it, let me know. All right, I just want you to see if you can decide if these are polar. This is polar, okay, partial negative, partial positive. So what makes polar things dissolve in polar things? Those opposite charges. What makes polar things dissolve ionic compounds? Because ions are oppositely charged. Okay, so dissolving. Dissolving happens sometimes because of electrostatic attraction, positives and negatives. And we could talk about the different kinds of positives and negatives, but they're attracted to each other. Dissolving happens in nonpolar things because there's not much attractions, but they can slide past each other. So things with charges stick together, things without charges stick together. All right, so there's a mixing with nonpolar things because there's no opposite charges, so they can just slide right past each other. There is a little bit of attraction due to London dispersion forces. All right, so what if a dry cleaning solvent dissolves nonpolar oil? Well, what can you say about that solvent? It must be, you fill in the blank. All right, hopefully you said nonpolar. Okay, what if butanol dissolves in water? Then what does that tell you about butanol? It must be polar. Okay, just some practice. Okay, so question 1 was, will it dissolve? Question 2 is, well, how does it dissolve? Okay, so how do solutions form? Well, when you start, you have solute and you have solvent. Now, in order to get this to dissolve, first of all, the bonds between the particles holding the solute together have to be overcome. Okay, the attractions between one sugar molecule and another sugar molecule have to break in order for it to mix with the solvent. But wait, what's going on in the solvent? Same thing. The bonds between solvent and other solvent molecules have to break. Those attractions have to be overcome so that the solute can mix with it. Okay, So then break the solute attractions, break the solvent attractions, and form new attractions between solute and solvents. Okay? Sounds simple, but it's a key concept to understanding why it works. Okay? So there are some ionic compounds that don't dissolve. What? We just said that ionic compounds have what's that? Ionic compounds have opposite charges. Water is polar, kind of negative, kind of positive. So water can attract the positive ions and the negative ions because it has opposite sides. But wait, some ionic compounds don't dissolve. Well, think about this. You already have your date to KOH, right? You guys, a pretty strong bond, going to KOH, pretty strong bond. So you're going to stick together. All right, so that means you won't dissolve in water because you're sticking together. Just like some ionic compounds have strong enough attraction to stick together even though water's around. Okay, how do you know which ionic compounds will and won't dissolve? Solubility rules. Okay, so don't forget that. We'll look at them. Now, the truth about solubility is that everything can dissolve somewhat, but the solubility rules tell us that those things that are on the rules that can't dissolve, that the ones that precipitate, have pretty strong attractions for the ions compared to the attractions to water. Okay, so remember these? We said that these types of things are pretty water soluble, so are compounds with these in them. Okay, compounds with these in them are pretty soluble unless there was silver, mercury, and lead, and so that means the attraction of silver and chloride is stronger than the attraction of those ions for water, or water's attraction for those ions. Okay, these things are pretty insoluble, which means that the attractions for compounds with carbonate in them are pretty strong, even stronger than water's attractions. But don't forget that things, even though it says insoluble, they really are a little bit soluble. We'll talk about that. Okay, so that was all ionic compound stuff, right? But there's other kinds of compounds too, molecular compounds. When you put sugar in water, it dissolves. Okay, you know it, you taste it, yay, Kool-Aid. Okay, so what's happening there? Well, the sugar molecules dissolve and the sugar-sugar attractions break, and then the water surrounds each sugar molecule. Okay, so if we had to write that in an equation form, we have solid sugar, arrow, turns into aqueous sugar. What? Yes, the only difference is that the solid is now each piece of solid, each tiny molecule is surrounded by water molecules. Okay, surrounding the sugar molecules are water molecules, so they're not attracted together as sugar because water's in between them. Okay, so if you wanted to draw what's called the dissolving equation, you start with the thing together in its liquid, gas, or solid state, and then after that, you write down what happens. Okay, so I want you to try those, and we'll get to it in class. All right, so that was molecular dissolve. Ionic compounds do more than just dissolve. Ones that are soluble turn into their ions when they dissolve. They don't stay together as a whole thing and get surrounded by water. They break into their ions, and each ion gets surrounded by water, so this is called dissociate. So, what kind of compounds dissolve in water? Ionic and polar. What kind of compounds dissociate? Ionic. They dissolve and dissociate. So if NaCl dissolves in water, the Na ions get surrounded, and the Cl ions, Cl minus ions, get surrounded, and they're not connected to each other anymore. They're surrounded by water. Okay, the water's got a kind of negative charge, kind of positive charge, kind of positive charge, kind of negative charge. So then water molecules surround them. This is called solvation. Those ions are being solvated. Okay, and because they're broken apart, they're dissociated. So water surrounds them, solvation, broken apart, dissociated. Okay, so ionic dissolving equations have to show the ions as products. So here's our sodium chloride, here's our sodium ions dissolved in water, and our chloride ions dissolved in water, surrounded by water each ion. All right, these apply to soluble compounds, and remember, all compounds are soluble to an extent. We'll keep talking about that. So what we call dissolving equation shows the starting substance not dissolved, the ending substance aqueous, surrounded by water. There's another kind of equation called a net, I said it, net ionic equation. This net ion equation shows you precipitate when it forms. So they're opposite of dissolving. So look, if you had silver ions in one solution and you mix them together with chloride ions from a different solution, those ions would find each other and make a silver chloride precipitate. When would that happen? In a double replacement reaction. Why don't you see a whole double replacement reaction here? Because these just represent the ions that come together to make the solid. A net ionic equation is what you net. It's your final, what you take home is a solid. So let's talk about net in economic terms, all right? Your take-home pay is your net. Your precipitate is your net. A net ionic equation shows only the ions that make the precipitate, okay? Dissolving equation shows it dissolving and breaking into aqueous ions. Net ionic shows what you bring home, which is the solid. Okay, so you could practice too, all right? Calcium chloride dissolving. What would you have on this side? All right, you fill it in. Magnesium nitrate dissolving. What would you have on this side? Now, be careful with these subscripts. Chloride ions. Check a periodic table. It's Cl minus. So what does this mean? What does that mean? That means that in front of the chloride ions, you would put a 2 Cl minus. Why? Because every time this breaks apart, you get one calcium ion with a +2 charge, and you get 2 chloride ions. What shows dissolving is aqueous. Okay, you try the magnesium nitrate one. Don't forget, it makes ions. So you make sure you know your ions, polyatomics, okay? Now, two solutions can mix to form a precipitate. So if you have sodium and chloride, we already did this, redo it so you can see. If you have barium and nitrate in a solid form, you get aqueous barium and nitrate ions. All of these ions, if you mix solutions of these two things together, would be in that solution. If you mixed them all, you'd get 4 different kinds of ions. But some of these ions might find each other in that solution and make what's called a solid or precipitate. So which ones would find each other? Here's how you decide. Check solubility rules. Check solubility rules. Solubility rules to see which ones are the least soluble. Okay, so when you check the rules, you're going to find that barium and chloride want to come together to make a solid because there's not very soluble. So if there's barium ions and chloride ions around, they will have more attraction for each other than the water has for them. So you'd get a barium chloride precipitate when solutions, all of those ions are mixed together. Okay, so just to remind you, when water attacks, what kind of compound is this? Ionic. And what kind of compound is this? Covalent. How do I know? Well, here's water. Here's the compound. Water surrounding it. Here's what. See all these waters around it? But this compound is still together. Okay. Here's the ionic compound. When water surrounds it, the ions break into their positive and negatively charged things. Okay, so conducting electricity helps us decide what kind of solution dissolved, what kind of things dissolve to make the solution. So, what does electricity mean? Movement of charged particles. Ionic compounds have ions that can move, not when they're solid, but when they're dissolved. Okay, molecular compounds don't have ions. Hey, that's crazy. See that? That's like an upside down thing. All right. Molecular compounds don't have any ions. So because ionic compounds dissolve to form ions, they conduct electricity, and that's called an electrolyte. Vocab, vocab, vocab. Okay, molecular compounds are called non-electrolytes. Why? Because when they dissolve, they don't have ions, so they don't conduct electricity. Vocab, vocab, yeah. All right, so you got to know the definitions and know how they apply. All right, hey, look at this. This is a solution, okay, and it is not conducting electricity because there's no ions in it. This is a solution that is conducting electricity, but there's not a lot of ions. This is a solution that's conducting a lot of electricity because there's a lot of ions. What's surrounding these ions? Water, water, water. Okay, all around is water. Okay, so please read the book. You're like, this was a lot of talking and a lot of writing. All right, these books will help you. It's called textbook. Read it. Okay. Solution is a homogeneous mixture of many different states. Make sure you can do examples for each. Solute, you get dissolved, so it's going to be a small part. Solvent is the big part, but both of them together make the solutions. Okay. Dissolving can be represented with an equation. Okay? Like dissolves like. Polar dissolves polar. Nonpolar dissolves nonpolar. Polar dissolves ionic. Okay? Make sure to use soap. Think if you can figure out what that means. Okay? It has to do with like dissolves like. And I realize there's a lot of writing in these notes, but I think you'll be safe and sound from this tidal wave of fun chemistry. All right? These are the 3 objectives we looked at. Can you do it? I think you can. All right? You'll be safe and sound. Oh my gosh, Harbin, stop saying that. But hopefully you will, and hopefully have a great day. Peace out.